Before we begin tonight's journey through the cosmos, I want to ask for your support. If you're enjoying this content, please use your hype points on this video. It helps the channel grow more than you could possibly know. If you're listening on Spotify, leaving a review makes an incredible difference for us. And if you feel like it, drop a comment telling us what time it is where you are and where in the world you're listening from. We absolutely love seeing where everyone is tuning in from across the globe. Finally, if you enjoy these deep dives into the mysteries of our universe, please consider subscribing. It means everything. Now, let's begin. 100 Relaxing Facts About Stars. Close your eyes and imagine standing in a field far from any city. The air is cool against your skin. The ground beneath you is solid and still, covered in soft grass that bends gently in the night breeze. Above, stretching endlessly in every direction, is the night sky. It arches over you, like an infinite dome, curving down to meet the horizon on all sides. At first, you see only darkness. Your eyes are adjusting. The world is quiet except for the soft rustle of wind through grass, the distant call of a night bird, the steady rhythm of your own breathing. But then slowly, one by one, pinpricks of light begin to appear. A handful at first, the brightest ones piercing through the darkness. Then dozens more, filling in the gaps. Then hundreds, revealing patterns and clusters you had not noticed before. Then thousands, until the sky is filled with more points of light than you could ever count, each one a star, each one a sun, burning across distances so vast that the light reaching your eyes tonight began its journey long before you were born, perhaps before your grandparents were born, before your country existed, before humans had discovered fire. These are not decorations scattered across some celestial dome. They are not paintings or projections or reflections of some earthly light. They are real. They are massive spheres of fire, each one hundreds of thousands or millions or even billions of miles wide, floating in the silent void of space, separated by distances that defy comprehension. Between you and the nearest star beyond our sun lies an emptiness so vast that if you could travel at the speed of the light, faster than anything else in the universe, it would still take more than 4 years to arrive. And most of the stars you see are much, much farther away than that. For as long as human beings have existed, we have looked upward. Long before we built cities or invented writing or discovered the wheel, we were watching the stars. Our ancestors, sitting around fires on ancient savannas, watched these same lights wheel slowly across the heavens. They noticed that some stars moved in patterns, returning to the same positions season after season, year after year. They told stories about them, weaving myths and legends into the random scatter of distant suns. They navigated by them, using their positions to cross deserts and oceans without ever losing their way. They wondered what they were, gods perhaps, or distant fires, or holes in the fabric of heaven through which divine light shone. And now, thousands of years later, after centuries of observation and mathematics and scientific inquiry, we know. We have measured them, categorized them, understood their life cycles and their deaths. We have learned that stars are not eternal, but are born and live and die like everything else in the universe. We have learned that they are made of the same elements that make up our bodies. We have learned that we are made from them, that every atom in our bodies heavier than hydrogen was forged inside a star billions of years ago and scattered into space when that star died. We are, quite literally, made of stardust. We are the universe looking back at itself. Tonight, you will hear 100 facts about stars, but this is not a lecture. This is not a test. This is not something you need to study or memorize or review later. This is a meditation, a journey, a gentle descent into the vastness of space and time. Each fact will be delivered slowly, gently, like stones placed carefully into still water, each one sending out ripples that fade softly into silence before the next one arrives. You do not need to memorize them. You do not need to quiz yourself later or prove you were paying attention. You need only to listen and to let the vastness of the universe wash over you like a wave, slowly and peacefully, carrying you wherever it will. Some of these facts will fill you with wonder. Some will make you feel small, but in a comforting way. The smallness of being part of something infinitely larger than yourself. Some will simply be interesting, curious details about the way the cosmos works, and some you may not remember at all, and that is fine. The purpose is not retention. The purpose is relaxation. The purpose is to step outside your daily concerns, your deadlines and worries and plans, and to remember that you exist in a universe that is ancient and vast and beautiful and ongoing. So settle in. Get comfortable. Close your eyes if you wish. Breathe slowly. Let go of whatever tension you are carrying. The stars have been here for billions of years. They will be here for billions more. They are in no hurry. Neither are we. Let us begin. Chapter 1. What stars are. Stars are massive spheres of gas, not small clouds, not flickering flames, not anything you can hold or touch or comprehend by the standards of everyday experience. Each star is an entire world of matter, held together by its own gravity, burning steadily across the void. The Sun, which lights our days and warms our world, is a medium-sized star, and yet it contains 99% of all the mass in our entire solar system. All the planets, moons, asteroids and comets combined make up only 1%. The Sun is so large that more than 1 million Earths could fit inside it. And the Sun is not particularly large, as stars go. It is average, ordinary. There are stars hundreds of times larger. Stars are made mostly of hydrogen and helium. These are the simplest elements in the universe, the first elements to form after the Big Bang, the building blocks from which all other matter eventually forms. Hydrogen is the most abundant element in the cosmos, making up about 73% of all normal matter. Helium makes up about 25%. Everything else, carbon, oxygen, nitrogen, iron, gold, silver, all the elements that make up planets and people, accounts for less than 2%. Stars are creation engines, forges of complexity. They take simple elements and through the intense heat and pressure in their cores, fuse them into heavier, more complex elements. Everything solid you have ever touched was made inside a star. Stars are powered by nuclear fusion, deep. In their cores, where temperatures reach 10 million degrees or more, hydrogen atoms collide with such force that they fuse together, forming helium. This process releases energy, enormous, almost unimaginable amounts of energy. Every second, the Sun converts about 600 million tons of hydrogen into helium. In the process, about 4 million tons of matter are converted directly into energy, according to Einstein's famous equation. That energy radiates outward, eventually reaching us as light and heat. The light you see from the Sun left its core hundreds of thousands of years ago, bouncing around inside the Sun, working its way outward, until finally it emerged from the surface and crossed the void of space in just over 8 minutes to reach your eyes. The energy released by fusion is what makes stars shine. It radiates outward from the core through layers of superheated gas until it finally escapes into space as light and heat. This is the light you see when you look up at night. This is the warmth you feel on your skin when you stand in sunlight. This is the energy that powers all life on Earth. Photosynthesis, weather, ocean currents, the entire biosphere. All of it traces back to the fusion reactions happening deep inside the Sun's core right now, at this very moment, as you listen to these words. Stars shine for millions or billions of years. The smallest stars, the red dwarfs, can burn steadily for trillions of years, far longer than the current age of the universe, which is only about 14 billion years old. No red dwarf has ever died of old age. There has not been enough time. Larger stars burn faster, consuming their fuel at a tremendous rate, shining brighter but living shorter lives. A blue supergiant might burn through its fuel in only a few million years. But even that is a long time by human standards. These stars outlast civilizations. They outlast species. They outlast entire epochs of geology and evolution. Gravity holds stars together. Without gravity, the immense pressure and heat inside a star would tear it apart instantly. blowing it to pieces in a catastrophic explosion. But gravity pulls inward, compressing the gas, keeping everything bound into a sphere. Gravity is relentless. It never tires. It never stops. It pulls constantly, holding billions upon billions of tons of superheated gas in a perfect balance. Inside a star, heat and pressure are constantly balanced. The outward push of energy from fusion balances the inward pull of gravity. This balance is what allows a star to remain stable for so long. It is a tug of war that can last billions of years, neither side winning, both forces matched perfectly. But when the fuel runs out, when the fusion reactions slow, the balance tips, gravity wins, and the star begins to change. Every visible star is extremely distant. The stars you see at night are not nearby. They are not just outside our atmosphere or floating a few hundred miles above Earth. Even the closest ones are separated from us by trillions of miles. Space is vast beyond human comprehension. The distances are so great that normal units of measurement, miles, kilometers, become meaningless. Instead, astronomers measure distance in light years, the distance light travels in 1 year. Light moves at 186,000 miles per second, fast enough to circle the Earth more than 7 times in a single second. And yet, even travelling at that incredible speed, it takes years to cross the distance to the nearest stars. Even the closest star beyond our Sun is incredibly far away. Proxima Centauri, the nearest star to Earth after the Sun, is more than 4 light-years away. That means light, travelling at 186,000 miles per second, takes more than 4 years to cross that distance. In miles, that is about 25 trillion miles. The fastest spacecraft humanity has ever built, Voyager 1, is travelling at about 38,000 miles per hour. At that speed, it would take more than 70,000 years to reach Proxima Centauri. The star you can see from your backyard is, in practical terms, unreachable. Stars are born, live, and die. They are not eternal fixtures painted on the dome of heaven. They are not unchanging lights that have always existed and will always exist. They form from clouds of gas and dust. They ignite. They burn for millions or billions of years. They change, evolving through different stages as they age, and eventually they fade or explode, returning their material to space. Like all things in the universe, stars move through cycles of creation and destruction. They are temporary, finite, mortal, and yet they last so much longer than we do that they might as well be eternal. Chapter 2. Starbirth. Stars form inside nebulae. A nebula is a vast cloud of gas and dust, spread across light years of space, floating silently in the darkness between older stars. If you could see a nebula up close, it would appear almost empty. The gas is so diffuse that it is thinner than the best vacuum we can create on Earth. And yet these clouds contain enough material to form thousands of stars. They are enormous, beautiful, and ancient. Nebulae are the cradles of creation. They are ancient remnants of earlier stars mixed with primordial hydrogen left over from the beginning of the universe. When a star dies, it returns its material to space, either gently, shedding its outer layers, or violently, exploding as a supernova. That material mixes with the interstellar medium, the thin gas that fills the space between stars. Over millions of years, this gas collects into clouds, and inside these clouds, gravity begins to pull matter together. Creation begins again. Gravity causes collapse. In certain regions of a nebula, where the gas is slightly denser than average, perhaps because a shock wave from a nearby supernova has compressed it, gravity begins to pull more and more material inward. A clump forms, then a knot, then a core. As more gas falls inward, the gravitational pull increases, attracting even more material. It is a feedback loop. Collapse begets collapse. What begins as a slight density fluctuation becomes an unstoppable contraction. Heat builds at the core. As gas collapses inward, it compresses, and when gas compresses, it heats up. This is a basic law of thermodynamics. The temperature rises, the pressure increases, the core becomes a furnace, glowing first red, then yellow, then white hot. But it is not yet a star. Not yet. It is only a protostar, a star in the process of formation, still gathering mass, still collapsing. Fusion begins. When the core reaches a critical temperature, around 10 million degrees, hydrogen atoms begin to fuse together, forming helium and releasing energy. This is the moment of ignition. This is when a protostar becomes a true star. Energy floods outward from the core, light escapes, the collapse halts, balanced now by the outward pressure of fusion. A star is born. It will shine for millions or billions of years. The moment a star ignites is called stellar ignition. It is a quiet event, in cosmic terms, happening in silence across the void. No one hears it. No alarm sounds, no trumpet blares. But the universe gains a new source of light, a new point of energy, a new engine of creation. And if that star has planets, which many do, those planets will be bathed in starlight for the first time. Day will break on worlds that have never seen a sunrise. Many stars form in clusters. When a nebula collapses, it often forms not one star, but dozens or hundreds or thousands, all born from the same cloud, all siblings in the darkness. These are called star clusters. Over millions of years, the stars drift apart, their mutual gravitational bonds weakening, until eventually they scatter across the galaxy. But for a time, they stay together, a family of young stars moving through space as one. Some stars form alone. Not all stars have siblings. Some condense in isolation from smaller clouds or quieter regions of space and spend their entire lives drifting alone through the void. These are solitary stars wandering the galaxy, separated from their birthplace, untethered to any cluster or companion. Perhaps they are lonely, or perhaps they are free. Star formation takes millions of years. The collapse of a nebula, the heating of a core, the ignition of fusion. All of this happens slowly by human standards. A star's birth is not an instantaneous event. It is a process measured in eons, unfolding over timescales so long that entire civilizations could rise and fall in the time it takes for one star to form. New stars are still forming today. Right now, at this very moment, in distant nebulae scattered across the Milky Way and beyond, new stars are being born. Clouds are collapsing. Cores are heating. Fusion is beginning. The universe continues to create endlessly, tirelessly, producing new lights to replace the old ones that have faded and died. Chapter 3. Types of stars. Stars vary in size. Some stars are much smaller than our Sun. Others are hundreds of times larger. The smallest known stars are barely larger than Jupiter, the giant planet in our solar system. They are so small that they teeters on the edge between being a star and being a failed star, a brown dwarf. The largest known stars are so enormous that if you placed them where the Sun is, their outer atmosphere would extend past the orbit of Jupiter, swallowing Mercury, Venus, Earth, Mars, and the asteroid belt entirely. Size determines everything about a star: its lifespan, its temperature, its brightness, its colour, and its ultimate fate. Small stars burn slow and cool, lasting for trillions of years. Large stars burn hot and fast, exhausting their fuel in just a few million years before exploding catastrophically. Some stars are much larger than the Sun, giant. Stars, supergiant stars, hypergiant stars. These are behemoths, so large that if you could stand on their surface, the horizon would stretch so far away that you could not see the curvature. Uy-Scuti, one of the largest known stars, has a radius about 1,700 times larger than the Sun. If you replace the Sun with Uy-Scuti, its surface would reach beyond the orbit of Saturn. These massive stars are rare, making up only a tiny fraction of all stars, but they are so bright that they can be seen from enormous distances. They burn through their fuel at a prodigious rate, converting millions of tons of hydrogen into helium every second, shining with the light of millions of suns. Other stars are much smaller. Red dwarfs, for example, are often only a tenth the mass of the Sun, and only about 1/10 the diameter. Some are even smaller, with masses as low as 8% of the Sun's mass. These tiny stars glow faintly, producing only a fraction of a percent of the Sun's light output. You could stand on a planet orbiting a red dwarf at the same distance Earth orbits the Sun, and the star would appear dim and orange-red in the sky, providing only a fraction of the heat and light we receive from our Sun. And yet these stars are incredibly numerous. They make up about 70% of all stars in the galaxy. They are the workhorses of the universe, the quiet, unassuming background against which the drama of larger stars plays out. Red stars are cooler. A red star's surface temperature is lower than that of a yellow or white star. Where the Sun's surface temperature is about 10,000 degrees, a red dwarf might have a surface temperature of only 6,000 degrees or less. Red light means less heat. These stars glow like embers rather than flames, casting a dim, ruddy light across any planets that might orbit them. On a planet orbiting a red dwarf, the sky would be bathed in a perpetual sunset glow, orange and red, with shadows that are long and soft. Photosynthesis would be different on such a world. Plants might evolve to be black rather than green, absorbing every possible photon of the weak light. Blue stars are hotter. Blue and white stars burn at extremely high temperatures. Their surfaces can reach 20,000, 30,000, even 50,000 degrees. They shine fiercely, pouring out vast amounts of ultraviolet radiation, flooding their surroundings with energy. These stars are young, massive, and short-lived. They burn so hot and so bright that they exhaust their fuel in just a few million years, a blink of an eye in cosmic terms. But during their brief lives, they dominate their surroundings, illuminating entire nebulae, stripping away the atmospheres of nearby planets with their intense radiation, and ultimately ending in spectacular supernova explosions that seed the galaxy with heavy elements. White stars are extremely dense. White dwarfs are the remnants of stars that have shed their outer layers. What remains is a core of compressed matter, incredibly hot, incredibly small, slowly cooling over billions of years. A white dwarf is typically about the size of Earth, but it contains about half the mass of the Sun. That means a teaspoon of white dwarf material would weigh several tons. The gravity on the surface of a white dwarf is about 100,000 times stronger than Earth's gravity. If you could somehow stand on the surface, you would be instantly crushed flat. White dwarfs are supported not by fusion or thermal pressure, but by electron degeneracy pressure, a quantum mechanical effect that prevents the electrons from being compressed any further. They are stable, inert, slowly radiating away their heat over trillions of years until they fade to black. Giant stars swell outward. As a star ages and runs low on hydrogen fuel in its core, it can expand dramatically, ballooning into a red giant hundreds of times its original size. The core contracts, heating up as it does. So, while the outer layers expand outward, cooling as they spread. The result is a star with a hot, dense core and a vast, diffuse envelope. Red giants are so large that their outer layers are only loosely bound by gravity. Material can drift off into space, carried away by stellar winds, forming glowing clouds around the star. Inside a red giant, the conditions are strange. The core might be hotter than the core of a main sequence star, while the surface is cooler, and the space in between is filled with convection currents that carry heat from the interior to the surface. Dwarf stars are compact. Despite their name, dwarf stars are not necessarily small in absolute terms. Some are still larger than Earth, larger than Jupiter, but they are compact compared to giants and supergiants. A white dwarf, as we have discussed, is incredibly dense, packing a huge amount of mass into a small volume. A red dwarf is small and low mass, but still much larger than any planet. A brown dwarf is intermediate, too small to sustain hydrogen fusion, but still glowing from the heat of its formation. These compact stars are common, numerous, and long-lived. They are the background stars of the galaxy, the ones that will still be burning long after all the bright, massive stars have died. Most stars are red dwarfs. In the Milky Way, the most common type of star is the red dwarf. They are small, dim, and incredibly long-lived. They burn their fuel so slowly, so efficiently, that they can last for trillions of years, far longer than the current age of the universe. They are the quiet majority, the unseen multitude. Despite making up 70% or more of all stars, not a single red dwarf is visible to the naked eye from Earth. They are simply too dim. All the stars you can see in the night sky without a telescope are either larger or hotter, or closer than average. The typical star in the galaxy is invisible to human eyes, a faint red ember drifting through the darkness. Some stars pulse rhythmically. Variable stars change in brightness over time, expanding and contracting in regular cycles. Cepheid variables, for example, swell and shrink with periods ranging from a few days to a few months, brightening and dimming as they do so. The period of pulsation is directly related to the star's intrinsic brightness, which makes these stars incredibly useful as cosmic distance markers. By measuring how fast a Cepheid pulses, astronomers can determine how bright it truly is. By comparing that to how bright it appears, they can calculate how far away it is. These pulsating stars were key to discovering that the universe is much larger than our galaxy, that the fuzzy nebulae astronomers saw through their telescopes were actually other galaxies, millions of light years away. Some stars spin rapidly. Neutron stars, the dense remnants of massive stars, can spin hundreds of times per second, emitting beams of radiation like cosmic lighthouses. These are called pulsars, and they were discovered in the late 1960s by a graduate student named Jocelyn Bell Burnell. The signals were so regular, so precise, that for a brief time astronomers wondered if they might be artificial, signals from an alien civilization. But they were natural, neutron stars, only about 20 kilometers across, spinning at incredible speeds, sweeping beams of radio waves across space. Some pulsars spin so fast that their surfaces are moving at a significant fraction of the speed of light. They are among the most extreme objects in the universe, with densities so high that a teaspoon of neutron star material would weigh as much as a mountain. Some stars exist in pairs. Binary star systems are incredibly common. Two stars orbiting a shared centre of gravity, bound together by gravity, travelling through space as companions. Sometimes the two stars are similar in size and brightness. Sometimes one is much larger than the other. Sometimes they orbit close together, completing an orbit in just a few days. Sometimes they are separated by hundreds of astronomical units, taking thousands of years to orbit each other. In some binary systems, the stars are so close that material can flow from one to the other, transferring mass, altering evolution, sometimes triggering explosions. These interacting binaries are among the most dynamic systems in the galaxy. Binary systems are common. More than half of all stars exist in binary or multiple systems. Lone stars like our Sun are actually somewhat unusual. Most stars are born with siblings, and many remain gravitationally bound throughout their lives. Some binaries are wide pairs, separated by thousands of astronomical units, barely interacting. Others are close binaries, orbiting each other in days or even hours, their surfaces nearly touching, distorted by tidal forces into elongated teardrop shapes. The dynamics of binary systems are complex and fascinating, and they give rise to phenomena that cannot occur in single stars: eclipses, mass transfer, tidal synchronization, and various types of stellar explosions. Triple systems exist. Some star systems contain 3 stars, all orbiting each other in complex intertwined paths. The dynamics are chaotic, beautiful, and mathematically intricate. Sometimes 2 stars orbit each other closely while a third orbits both from a distance. Sometimes all 3 orbit in a complex hierarchical arrangement. These systems are less common than binaries, but they are not rare. Astronomers have discovered thousands of triple star systems. If you lived on a planet in a triple star system, the sky would be a constantly changing tapestry of suns, with different combinations rising and setting at different times, creating a complex cycle of day and night that might take years to repeat. Stars often have companions. Whether binary, triple, or part of larger clusters, stars are rarely truly alone. The universe favours connection over isolation. Even stars that appear solitary may have faint companions that are hard to detect. Many nearby stars once thought to be single have turned out, upon closer inspection, to have brown dwarf companions or planetary systems or faint red dwarf companions orbiting at great distances. The gravitational dance of stars is one of the fundamental patterns of the cosmos, repeated billions upon billions of times across the galaxy. Chapter 4. The Life of a Star. Stars spend most of their lives stable. For the majority of a star's existence, often 90% or more of its total lifespan, it burns hydrogen steadily in its core, maintaining equilibrium between gravity and internal pressure. Astronomers call this the main sequence phase. This phase can last billions of years for a star like our Sun. During this time, the star changes very little. It shines at roughly the same brightness, maintains roughly the same temperature, stays roughly the same size. It is predictable, reliable, steady. This is the calm adulthood of a star's life, the long, stable period between birth and death. Fuel slowly runs out. No matter how vast a star's reserves of hydrogen, no matter how efficiently it burns, eventually the core begins to deplete. The hydrogen at the centre gets converted to helium, and helium does not fuse as easily. The rate of fusion slows, the balance shifts, the outward pressure decreases slightly, gravity gains the upper hand, and the star begins to change. For a star like the Sun, this will happen in about 5 billion years. The Sun is currently middle-aged, about halfway through its stable main sequence life. Smaller stars fade gently. Red dwarfs and other small stars do not explode when they die. They do not go out in a blaze of glory. They simply burn through their fuel, dim gradually over billions of years, and eventually cool into dark remnants called black dwarfs. These are dead stars, no longer producing energy, slowly radiating away their remaining heat into the cold of space. They will persist for trillions upon trillions of years, cooling gradually, fading into the background radiation of the universe. They are the final quiet end of small stars, a gentle fade to black. Larger stars expand dramatically. When a massive star exhausts the hydrogen in its core, it does not simply fade. Instead, it begins fusing heavier elements, helium into carbon, carbon into oxygen, oxygen into silicon, and so on, building up layers like an onion. The core contracts, growing hotter and denser with each new phase of fusion. Meanwhile, the outer layers expand outward, swelling to enormous size. The star swells into a red giant or supergiant, growing hundreds or even thousands of times larger than it was during its main sequence phase. Red giants form when stars age. Our own Sun will become a red giant in about 5 billion years. When that happens, it will expand outward, possibly engulfing Mercury, Venus, and perhaps even Earth. It will glow, red and enormous in the sky, filling half the horizon. If Earth survives, its oceans will boil away, its atmosphere will be stripped, and its surface will become molten. The Sun's red giant phase will last for about 1 billion years before it sheds its outer layers and contracts into a white dwarf. This is the inevitable fate of stars like our Sun. Expansion, then contraction, then a slow fade over billions of years. Some stars shed outer layers, as red giants pulse and swell, expanding and contracting in irregular rhythms. They can lose vast amounts of material into space. These layers drift outward, forming glowing shells called planetary nebulae. The name is misleading. They have nothing to do with planets. Early astronomers viewing them through primitive telescopes thought they looked like planets, hence the name. But they are actually the cast-off outer layers of dying stars, glowing in the ultraviolet light from the exposed hot core at the centre. Planetary nebulae are beautiful, intricate, and temporary. They last only about 10,000 years before dispersing into the interstellar medium. Nebulae are recycled material. The gas and dust shed by dying stars do not disappear. They do not vanish into nothingness. They mix with interstellar clouds, enriching them with heavier elements created during the star's lifetime. Over millions of years, these enriched clouds collapse to form new stars and planets. Second-generation stars have more heavy elements than first-generation stars. Third-generation stars have even more. Our Sun is a third-generation star, formed from material recycled from earlier stars. The carbon in your body, the oxygen you breathe, the iron in your blood, all of it came from stars that died billions of years ago. Massive stars explode as supernovae. When a star much larger than the Sun exhausts its fuel, when it has fused elements all the way up to iron, it can go no further. Iron fusion absorbs energy rather than releasing it. The core suddenly has nothing to support it against gravity. In less than a second, the core collapses and the outer layers rebound in a catastrophic explosion called a supernova. For a brief time, a single supernova can outshine an entire galaxy of hundreds of billions of stars. The explosion releases more energy in a few seconds than the Sun will produce in its entire 10 billion year lifetime. Supernovae are among the most violent events in the universe. Supernovae create heavy elements. The intense heat and pressure of a supernova forges elements that cannot form inside normal stars. Gold, silver, platinum, uranium, all the elements heavier than iron, are created in the moments of a supernova explosion. These elements are scattered into space, carried outward on the expanding shockwave. They mix with interstellar gas and eventually become part of new stars and planets. Every gold ring, every silver coin, every piece of uranium, all of it was forged in the heart of an exploding star. These elements are needed for life: carbon, oxygen, nitrogen, iron, phosphorus. All the building blocks of planets and living organisms were forged inside stars and released in supernovae or stellar winds. Without stellar nucleosynthesis, without the death of stars, there would be only hydrogen and helium in the universe. There would be no rocky planets, no water, no air, no life. We exist because stars died. Our atoms are recycled stardust. We are not separate from the cosmos. We are part of it. Star deaths seed new stars. The material ejected by dying stars becomes part of new nebulae. From these clouds, enriched with heavy elements, new stars and planets form. These second and third generation stars can have rocky planets like Earth, planets with solid surfaces and liquid water and atmospheres thick enough to support life. Death feeds creation. Endings enable beginnings. The cycle continues, generation after generation across billions of years. Life comes from stardust. Every atom in your body heavier than hydrogen was created inside a star. Your bones, your blood, your breath, your DNA, all of it came from the furnaces of long-dead suns. You're not merely in the universe, you're a part of the universe. You're made of the same substance as stars. When Carl Sagan said we are made of star stuff, he was being literal. This is not poetry. This is physics. The universe constantly renews itself. Stars die. New stars are born. Nebulae collapse. Supernovae explode. Elements are forged and scattered and gathered again. The cycle continues endlessly, a cosmic rhythm of creation and destruction that has been playing out for billions of years and will continue for billions more. The universe is not static. It is dynamic, ever-changing, constantly renewing itself. Death is part of balance. Without the death of stars, there would be no heavy elements. Without heavy elements, there would be no planets, no oceans, no life. Destruction enables creation. Endings allow for new beginnings. This is true at every scale of the universe. Death is not an aberration. It is part of the natural order. It is necessary. Without it, there would be no change, no evolution, no complexity. Stars shape the cosmos. Through their lives and deaths, stars determine the structure and composition of galaxies. They create the elements. They enrich the interstellar medium. They compress gas clouds with their stellar winds and supernova shockwaves, triggering new star formation. They are the architects of the universe, the builders of complexity, the engines of change. Without stars, the universe would be a cold, dark, formless void. Stars bring light. Stars bring structure. Stars bring possibility. Chapter 5. Distance and Time. Stars are measured in light years. A light year is the distance light travels in 1 year, about 6 trillion miles, or about 10 trillion kilometers if you prefer, is a distance so vast that it becomes abstract, meaningless in human terms. You cannot drive a light year. You cannot walk it. You cannot even imagine it in any concrete sense. When we say a star is 10 light years away, we mean its light has been travelling through the empty void of space for 10 years to reach us. The photons hitting your eyes tonight left that star a decade ago, when the world was different, when you were younger, or perhaps not yet born. You're seeing the past. Every time you look at a star, you're looking backward through time. Light travels extremely fast. At 186,000 miles per second, or about 300,000 kilometers per second, light is the fastest thing in the universe. Nothing can move faster. It is the speed limit of reality, built into the fabric of space-time itself. At this speed, light can circle the Earth more than 7 times in a single second. It can travel from the Earth to the Moon in just over 1 second. It can cross the diameter of the solar system in about 11 hours, and yet, even at this incredible speed, crossing cosmic distances takes years, centuries, millennia, eons. The universe is so vast that even light, moving at the maximum possible speed, seems slow, yet distances remain vast. The fastest spacecraft humanity has ever built, Voyager 1, is travelling at about 38,000 miles per hour, which sounds fast until you realise that at this speed, it would take more than 70,000 years to reach Proxima Centauri, the nearest star beyond the Sun. 70,000 years. All of recorded human history is only about 5,000 years old. 70,000 years ago, Homo sapiens had only just begun to migrate out of Africa. The pyramids would not be built for another 65,000 years. Writing would not be invented for another 68,000 years. And Voyager, humanity's fastest messenger, would still be travelling through the void, not yet halfway to its destination. Space is incomprehensibly large. The distances defeat all intuition. Looking at stars is looking into the past. When you see a star 10 light years away, you're seeing it as it was 10 years ago. The light hitting your eyes left that star a decade before you saw it. If that star exploded 9 years ago, you would not know yet. You would still see it shining steadily in the night sky. The news of its death would not reach you for another year, travelling at the speed of light across the intervening void. Everything you see in the night sky is history. Some of it is recent history. Stars a few light years away, as they were a few years ago. Some of it is ancient history. Galaxies millions or billions of light years away, as they were millions or billions of years ago. When the universe was younger, when the Earth did not yet exist, when the first stars were just beginning to forge the heavy elements that would later become planets and people. Some stars no longer exist. When you look at very distant stars, some of them may have already died. Their light is still travelling through space, carrying the image of a star that is no longer there, but the star itself is gone. It may have exploded in a supernova thousands of years ago. It may have faded to a white dwarf millions of years ago. But its light is still racing outward at the speed of light, spreading in all directions, reaching new worlds for the first time, creating the illusion of presence long after the star itself has ceased to be. In a very real sense, stars can haunt the universe, their ghosts visible long after they have died. Their light still travels. Even after a star explodes or fades, its light continues outward at the speed of light, carrying information about a star that no longer exists. That light will travel for billions of years, crossing intergalactic voids, perhaps eventually reaching some distant civilization that looks up and sees it for the first time, never knowing that the star they are seeing is long dead, that they are seeing a ghost, an echo, a memory written in photons. Light does not stop, light does not decay, light simply travels forever until it is absorbed by something, a planet, a dust grain, an eye, a telescope. The Milky Way holds billions of stars. Our galaxy contains somewhere between 100 billion and 400 billion stars. The exact number is uncertain because many stars are too faint to detect, hidden behind dust clouds or too far away to see clearly. But the number is vast. That is more stars than there are people who have ever lived on Earth. If you tried to count them, one per second, it would take you thousands of years. And each one of those stars is a sun, potentially with its own planets, its own worlds, its own story. The Milky Way is not a simple collection of lights. It is a galaxy, a gravitationally bound system of hundreds of billions of stars, plus gas, dust, dark matter, black holes, and who knows what else, all orbiting a supermassive black hole at the centre. Other galaxies hold billions more. The Milky Way is just one galaxy among trillions in the observable universe. Each galaxy contains billions or trillions of stars. The Andromeda Galaxy, our nearest large galactic neighbour, contains about 1 trillion stars. The Triangulum Galaxy contains about 40 billion. Distant galaxies, photographed by the Hubble Space Telescope and the James Webb Space Telescope, contain billions upon billions of stars, each one too faint and distant to see individually, blurred together into a diffuse glow. And there are trillions of such galaxies, scattered across billions of light-years of space, each one a separate island universe, each one containing more stars than humans can comprehend. The universe contains countless stars. Estimates suggest there are more stars in the universe than grains of sand on all the beaches on Earth. Some estimates go even further, suggesting there are more stars than atoms in a handful of sand. The numbers become absurd, meaningless, ungraspable. But the point is clear. The universe is unimaginably vast, filled with unimaginable numbers of stars. Every direction you look, if you look far enough, you will see galaxies. Every galaxy contains billions of stars. The universe is not empty. It is full. It is teeming with stars, separated by vast distances, yes, but present everywhere, filling space with light and energy and possibility. Human numbers are insignificant by comparison. All of human history, every life ever lived, every empire risen and fallen, every war fought, every symphony composed, every act of kindness or cruelty. It all takes place on one small planet orbiting one ordinary star in one corner of one galaxy among trillions. We are insignificant in scale, and yet we are significant in other ways. We are the universe aware of itself. We are matter arranged in such a way that it can contemplate its own existence. We are rare, perhaps even unique. We are brief, but we are real. Our smallness does not diminish our meaning. It contextualizes it. We are tiny, yes, but we are part of something vast. Space is mostly empty. Despite the vast number of stars, the universe is overwhelmingly empty. The distances between stars are so great that space is nearly a perfect vacuum, emptier than the best vacuum chambers we can create on Earth. In interstellar space, there might be 1 atom per cubic centimetre. In intergalactic space, there might be 1 atom per cubic metre. This is emptiness beyond comprehension. If you shrank the sun to the size of a grain of sand, the nearest star would be another grain of sand 4 miles away. Everything in between, emptiness, silence, void. Stars are widely spaced. The average distance between stars in the Milky Way is about 5 light-years. That is about 30 trillion miles, or about 50 trillion kilometres. If you could somehow travel at the speed of light, it would take you 5 years to reach the next star, and that is just the average. In some regions of the galaxy, stars are more tightly packed. In globular clusters, for example, where thousands of stars are crammed into a sphere only a few light-years across. In other regions, stars are more widely separated, drifting alone through vast stretches of empty space. But on average, the galaxy is a sparse place, with far more emptiness than matter. Darkness dominates between them. The space between stars is not lit. It is cold, silent, and dark. If you could stand in interstellar space, floating between the stars, you would see stars scattered across the sky in all directions, but they would appear as mere points of light, no brighter than they appear from Earth. There would be no ambient light, no glow illuminating your surroundings. Everything around you would be perfectly black. The nearest star might be 5 light-years away, appearing as a bright point but providing no warmth, no illumination. you would float in absolute darkness surrounded by the cold vacuum of space. Stars are islands of light in an ocean of void. The darkness is fundamental. The light is the exception. Silence fills the gaps. There is no sound in space, no air to carry vibrations, no medium to transmit waves. The universe is silent except where matter exists in sufficient density to transmit sound waves, on planets with atmospheres, inside stars, in dense nebulae. But in the space between, there is only silence. Perfect, absolute silence. A supernova could explode nearby, releasing more energy than the sun will produce in its entire lifetime, and you would hear nothing. You would see a flash of light. You might feel radiation hitting your body, but you would hear nothing. The explosion would be silent. Space is a silent place, and that silence is deeper and more complete than any silence you have ever experienced on Earth. Time stretches endlessly. Human lifespans are brief flickers compared to the life of a star. A human lives, on average, about 70 or 80 years. A star lives for millions, billions, even trillions of years. Stellar timescales are measured in epochs so long that human history is barely a moment. The sun has been shining for about 4.5 billion years. It will continue to shine for another 5 billion years. All of human history, from the first stone tools to the present day, represents about 1/10,000,000th of the sun's total lifetime. We exist in an instant, a fleeting moment in the vast sweep of cosmic time. Stars exist across eons, burning steadily through ages so long that continents drift, species evolve and go extinct, and planets form and die. Chapter 6. Colour, Light and Motion. Stars appear to twinkle from Earth. The twinkling you see is not the star itself flickering. It is not the star varying in brightness or pulsating. It is caused by Earth's atmosphere, which bends and distorts the starlight as it passes through layers of moving air. The atmosphere is not uniform. It contains pockets of warmer and cooler air, regions of different density and pressure, all constantly moving, shifting, swirling. As starlight passes through these turbulent layers, it bends slightly, changing direction. From our perspective on the ground, this makes the star appear to shift position slightly, to brighten and dim, to shimmer and dance. It is beautiful. But it is also an illusion, a trick of the atmosphere. Twinkling is caused by atmosphere. In space, stars do not twinkle. They shine steadily. Astronauts in orbit, or on the moon, see stars as constant points of light, unwavering and still. There is no atmosphere to distort the light, no air to bend the photons. The stars shine with perfect constancy, like diamonds scattered across black velvet. This was one of the surprising observations made by the Apollo astronauts. The stars did not twinkle. They were still, fixed, eternal. It was strange and beautiful and somehow unsettling, this view of stars as they truly are, unfiltered by atmosphere. Stars move through space. Though they appear fixed in the sky, stars are in motion. They orbit the centre of the galaxy, moving at speeds of hundreds of thousands of miles per hour. The Sun, for example, is travelling at about 500,000 miles per hour as it orbits the galactic centre. It takes the Sun about 225 million years to complete one orbit around the galaxy. The last time the Sun was in its current position in the galaxy, dinosaurs were just beginning to emerge on Earth. The next time it returns to this position, if Earth still exists, it will be 225 million years in the future, when the continents have drifted into new configurations, when new species have evolved, when perhaps intelligence has arisen elsewhere in the galaxy. Constellations slowly change. Over thousands of years, the stars in constellations shift position. The patterns our ancestors saw are not the patterns future generations will see. The Big Dipper, for example, looks very different now than it did 50,000 years ago, and it will look very different 50,000 years from now. The stars are moving relative to each other, each following its own orbit around the galaxy. Some are moving toward us, some away. Some are moving faster, some slower. Over time, the familiar shapes will distort, stretch, dissolve. New patterns will emerge. The sky is not fixed. It is fluid, changing, evolving on timescales longer than human memory but shorter than stellar lifespans. Some stars move rapidly. High-velocity stars have been flung out of their original orbits by gravitational interactions. They streak through the galaxy at speeds of hundreds or even thousands of kilometers per second, millions of miles per hour. Some are escaping the galaxy entirely, headed out into intergalactic space, never to return. These runaway stars were likely part of binary systems that came too close to a black hole or experienced a supernova explosion that kicked one star out at high velocity. They are cosmic outcasts, exiles, wanderers moving so fast that they will eventually leave the galaxy behind and drift alone through the void for billions of years. Others drift slowly. Most stars move in stately, predictable orbits around the galactic center. Their motion is real, but imperceptible on human timescales. You cannot see a star moving across the sky from night to night. The motion is too slow. The distance is too great. It takes years, decades, centuries to detect the movement. But it is there, constant and inexorable. The stars are not fixed points painted on the celestial sphere. They are independent objects, each moving through space on its own trajectory, following the gravitational pull of the galaxy as a whole. Colour reveals temperature. A star's colour tells you how hot it is. Red stars are coolest, with surface temperatures of around 6,000 degrees or less. Yellow stars, like the Sun, are medium, with temperatures around 10,000 degrees. White stars are hotter still, 15,000 to 20,000 degrees. Blue stars are hottest, with temperatures that can exceed 50,000 degrees. Colour is a thermometer written in light. The physics behind this is called blackbody radiation. Hot objects emit light at different wavelengths depending on their temperature. Hotter objects emit more blue light. Cooler objects emit more red light. By analysing a star's colour, astronomers can determine its surface temperature with remarkable precision. Brightness can change over time. Some stars are variable, changing brightness due to pulsations, eclipses by companion stars or other processes. The sky is not static, it is dynamic, filled with stars that brighten and dim, flare and fade. Some variable stars change on predictable schedules, pulsing rhythmically with periods of days, weeks or months. Others are irregular, flaring unpredictably due to instabilities in their atmospheres or eruptions on their surfaces. Still others vary because they are eclipsing binaries, two stars orbiting so close together that, from our perspective, they periodically pass in front of each other, blocking each other's light. Variable stars pulse. Cepheid variables expand and contract rhythmically, brightening and dimming in regular cycles. As the star expands, its surface area increases and it brightens. As it contracts, it dims. The cycle repeats endlessly, driven by instabilities in the star's interior. The period of pulsation, how long it takes to go from bright to dim and back to bright again, is directly related to the star's intrinsic luminosity. Brighter Cepheids pulse more slowly, dimmer Cepheids pulse more quickly. This relationship, discovered in the early 20th century, allowed astronomers to use Cepheid variables as standard candles, measuring distances to faraway galaxies and revealing the true scale of the universe. Light carries information. When we analyse starlight, we can determine a star's temperature, composition, speed, distance, and age. Light is a message written in photons. By spreading starlight into a spectrum, separating it into its component wavelengths, astronomers can see absorption lines, dark lines at specific wavelengths where the star's atmosphere has absorbed certain colours of light. Each element absorbs light at specific wavelengths, creating a unique fingerprint. By analysing these absorption lines, astronomers can determine what a star is made of: hydrogen, helium, carbon, oxygen, iron. They can also determine how fast the star is moving toward or away from us by measuring the Doppler shift of the lines. Light tells us everything we know about distant stars. It is our only connection to them, our only source of information, and it is enough. Chapter 7: Stars and Humans. Humans use stars for navigation. For thousands of years before maps or compasses or satellites, sailors navigated by the stars. The positions of constellations told them direction and latitude. In the northern hemisphere, Polaris, the North Star, hangs almost directly above the North Pole, providing a fixed point in the rotating sky. By measuring the angle between Polaris and the horizon, sailors could determine their latitude with remarkable accuracy. In the southern hemisphere, where Polaris is not visible, navigators use the Southern Cross and other constellations. Polynesian navigators crossed thousands of miles of open ocean using only stars, currents, and the flight patterns of birds, navigating with a precision that astounds modern sailors. The stars were their GPS, their map, their compass. And they worked. Calendars were based on stars. Ancient civilizations tracked the movement of stars across the sky to mark seasons, plan harvests, and schedule religious festivals. The stars told time on the grandest scale, marking the passage of the year through the changing constellations, visible at dusk. When certain stars appeared on the eastern horizon just before sunrise, a phenomenon called heliacal rising, it signaled specific times of year. The heliacal rising of Sirius, for example, coincided with the annual flooding of the Nile River in ancient Egypt, and the Egyptians used this as the basis for their calendar. The stars were predictable, reliable, eternal. They were perfect timekeepers. Seasons were tracked by constellations. When certain constellations appeared at dusk or dawn, people knew it was time to plant or harvest or prepare for winter. Orion rising in the evening sky meant winter was coming. The appearance of the Pleiades signalled the beginning of spring in some cultures, autumn in others. Farmers who could not read or write could still read the sky, using the stars to know when to plant wheat, when to harvest grain, when to prepare for frost. The sky was a calendar written in light, accessible to anyone with eyes and patience. Myths formed around patterns. Every culture that ever looked up at the stars saw patterns and told stories. Heroes, animals, gods, monsters, all projected onto the random scatter of distant suns. The ancient Greeks saw Orion the hunter chasing the Pleiades sisters across the sky. The ancient Chinese saw a celestial bureaucracy, with constellations representing emperors and officials and dragons. The Aboriginal Australians saw an emu in the dark spaces between stars. The Maya saw a crocodile, a turtle, a serpent. These stories were passed down through generations, encoding cultural knowledge, teaching moral lessons, explaining the world. The stars became a shared canvas for humanity's imagination, a place where cultures wrote their identities in myth. Cultures named the stars. Different civilizations gave different names to the same stars. Sirius, the brightest star in the night sky, was called the Dog Star by the Greeks, who saw it as part of the constellation Canis Major. The ancient Egyptians called it Sopdet and associated it with the goddess Isis. Different cultures had different names, different stories, different meanings, but they were all looking at the same lights, seeing the same stars, separated by thousands of miles and thousands of years, but united in their fascination with the night sky. Astronomy began with observation. The oldest science is the study of the stars. Humans have been watching the sky, recording patterns, and making predictions for tens of thousands of years. Long before we understood what stars were, we were tracking their movements, noting their positions, recording their patterns. Ancient observatories like Stonehenge in England, the Caracol at Chichen Itza in Mexico, and the astronomical instruments of ancient Babylon all testify to humanity's ancient obsession with the stars. We watched them because they were beautiful, yes, but also because they were useful. They told us when to plant, when to travel, when to celebrate. They gave structure to time. Telescopes revealed hidden stars. When Galileo first pointed a telescope at the sky in the early 17th century, he saw thousands of stars invisible to the naked eye. The Milky Way, which appears as a faint band of light stretching across the sky, resolved into countless individual stars too numerous to count. The universe grew larger in an instant, and it has continued to grow with every improvement in telescope technology. Modern telescopes can detect stars so faint that billions of them are invisible even through small telescopes. Each new generation of instruments reveals a deeper, more complex universe. Modern science decodes starlight. With spectroscopy, astronomers can analyze the light from a star and determine what it is made of, how hot it is, how fast it is moving, how far away it is, how old it is. We can read stars like books, extracting information from their light. This is a remarkable achievement. We are separated from stars by distances so vast that we cannot visit them, cannot touch them, cannot sample them. And yet by analysing their light we can understand them in extraordinary detail. We know what stars are made of. We know how they work. We know how they are born and how they die. All of this from light. Stars guided exploration. Polynesian navigators crossed the Pacific using only stars' currents and the flight patterns of birds. European sailors used stars to navigate the Atlantic and Indian Oceans, opening trade routes and connecting continents. The stars were maps written in the heavens, accessible to anyone who learned to read them, and they worked. People crossed oceans, traversed deserts, explored unknown lands, all guided by the steady, predictable light of distant suns. The stars were humanity's first guide to the world, and in some ways, they still are. Stars inspired wonder. Every child who has ever looked up at a clear night sky has felt it. The sense of smallness, of vastness, of mystery. The stars make us feel small, but not in a diminishing way. They remind us that we are part of something much larger than ourselves, something ancient and vast and ongoing. They inspire questions. What are they? How far away are they? Are there other worlds out there? Is there other life? These are the questions that drive science, that push us to explore, to discover, to understand, and they all begin with looking up at the stars and feeling wonder. Chapter 8: Star Systems and Planets. Many stars host planets. Planets are common around stars. Most stars in the galaxy likely have at least one planet orbiting them. The universe is full of worlds. Planetary systems are common. We have discovered thousands of exoplanets, planets orbiting other stars. These systems are as varied as the stars themselves. Some have gas giants, some have rocky worlds, some have both. Some planets orbit multiple stars. In binary star systems, planets can orbit one star or both. Imagine a sky with two suns, rising and setting at different times. Such worlds exist. Habitable zones vary. The habitable zone is the region around a star where liquid water can exist on a planet's surface. For red dwarfs, this zone is close. For blue giants, it is far. Each star defines its own zone of possibility. Not all stars are stable. Some stars flare unpredictably. Others vary in brightness. Young stars are turbulent. Old stars can pulse erratically. Stability is a gift, not a given. Stellar radiation shapes planets. The energy a planet receives from its star determines its climate, its atmosphere, its potential for life. Stars are not passive lights. They actively shape the worlds around them. Stellar winds exist. Stars emit more than light. They also emit streams of charged particles, stellar winds, that flow outward through space, interacting with planets and shaping their magnetic fields. Magnetic fields protect planets. A planet's magnetic field can shield it from stellar radiation and stellar winds. Without this protection, a planet's atmosphere can be stripped away over time. Stars influence habitability. A star's size, temperature, activity, and lifespan all affect whether life could arise on its planets. The right kind of star is essential. The Sun is one of many. Our Sun is not unique. It is a medium-sized, middle-aged yellow star, utterly ordinary. There are billions of stars like it in the Milky Way alone. Chapter 9: The Endless Sky. Stars existed before Earth. The first stars formed only a few 100 million years after the Big Bang. They shone for billions of years before our solar system even began to form. They will outlast humanity. The smallest stars will burn for trillions of years. Long after Earth is gone, long after the sun has died, these stars will still be shining. New stars will replace old ones. As stars die, new ones are born. The cycle continues. The galaxy renews itself. In 10 billion years, the Milky Way will look, very different, but it will still be filled with stars. The night sky is never the same. Every moment, stars are being born and dying. Light from distant events is arriving for the first time. The sky you see tonight is not the sky you saw last night. Fact 100. Stars are the universe remembering itself. Every star is a point where matter has gathered, where energy is being released, where creation is happening. Stars are how the universe becomes aware of its own existence. And when you look at them, when you see their light, you are part of that awareness. You are the universe looking back at itself. Outro. Return to the night. It is still night. The stars are still there, burning silently in the void, exactly as they were when we began. But now perhaps you see them differently, not as decorations scattered randomly across the sky, but as what they truly are: distant suns, ancient fires, forges of creation, each one with its own story, its own history, its own cycle of birth and life and death. Each one part of a vast cosmic cycle that has been unfolding for billions of years, long before Earth existed, long before life arose, long before humans looked up and wondered what those lights were. Some of the stars you can see tonight formed billions of years ago, before the solar system existed. They have been shining steadily all that time, through the formation of Earth, through the rise of life in the oceans, through the age of dinosaurs, through all of human history, through the rise and fall of every civilization. They were there when your great-grandparents were born. They will still be there when your great-grandchildren's great-grandchildren are gone. As dawn approaches, the stars begin to fade, not because they have stopped shining, but because the sun, our own star, our local furnace, is rising. Its light drowns out the others, flooding the sky with blue and gold. But the stars are still there, still burning invisibly in the daylight sky. You cannot see them, but they have not disappeared. They never disappear. They simply become invisible in the glare of closer light. And tonight, when darkness returns, when the sun sets and the sky deepens from blue to purple to black, they will reappear, one by one, exactly as they did at the beginning of this journey. The same lights humanity has watched since the beginning of our species. The same lights our ancestors navigated by, told stories about, wondered at. The same lights that will shine long after we're gone. Rest now. Sleep if you can. Let your thoughts drift like clouds across a still pond. Let the vastness of the universe hold you gently. You're small, yes, but you're part of something infinitely larger. You're made of atoms forged in the hearts of dying stars. You're the universe experiencing itself. You're a way for the cosmos to know itself. The stars will keep watch. They always have. They always will. And somewhere, right now, across the unimaginable distances of space, light is still travelling. Light from stars that died before Earth was born. Light that has been crossing the void for millions or billions of years, never stopping, never slowing, just travelling endlessly through the darkness. That light will reach some distant world millions of years from now, and perhaps someone, or something, will look up and see it for the first time, just as you looked up and saw starlight tonight. The universe is patient. It works on timescales that make human lifespans look like the blink of an eye. Mountains rise and erode away. Oceans form and dry up. Continents drift and collide. Species evolve and go extinct. And through it all, the stars keep shining. The universe is vast. So vast that human minds struggle to comprehend it. If you could travel at the speed of light, it would take 2.5 million years just to reach the nearest large galaxy. And there are billions of galaxies, each containing billions of stars. The numbers become meaningless, the scale defeats understanding, and yet here you are, a collection of atoms arranged in such a way that you can look up at those distant lights and understand, at least partially, what you are seeing. And you, for this brief moment, are part of it. Not separate from the universe, but within it, made of it, sustained by it, connected to every star, every planet, every atom of matter across all of space and time. You are made of the same hydrogen that formed shortly after the Big Bang. You're made of carbon forged in the cores of red giants. You're made of iron created in supernova explosions. You carry the history of the cosmos in your very atoms. That is what stars teach us if we listen. That we are not isolated, that we are not alone, that we are part of an ancient ongoing story that began 14 billion years ago and will continue for trillions of years to come. We are a chapter in that story, a brief, bright chapter, but a chapter. Nonetheless, good night, sleep well, and when you wake, remember, you're made of stardust. You always have been, you always will be. Before we begin tonight's journey, if you're enjoying this content, using hype points on this video helps the channel more than you possibly know. It truly makes a difference in reaching more listeners like yourself. If you're listening on Spotify, leaving a review helps us out so much. And if you'd like, comment what time it is for you and where in the world you're listening from. We absolutely love seeing where everyone is tuning in from across the globe. Finally, if you enjoy this content, subscribing keeps you connected to more stories like this one. Now let's begin. The desert wind moves differently at night. Across the Giza Plateau, where sand meets stone and silence becomes almost tangible, 3 monuments rise against the darkness. They've stood here for longer than most civilizations have existed. They've watched empires emerge and collapse. They've outlasted languages, religions, entire ways of understanding the world. Tonight we're going to walk slowly through the story of the Great Pyramid of Giza. Not the rush tour guide version, not the sensational documentary promising impossible secrets. Just a calm, methodical exploration of what we actually know about the last surviving wonder of the ancient world. Picture yourself standing on the plateau as the sun sets, the heat of the day finally releasing its grip on the sand. The Great Pyramid looms before you, massive beyond easy comprehension, its surface rough and weathered by millennia. This is where we begin our journey through time, through human ambition, through the intersection of faith and engineering that created something genuinely eternal. The temperature drops as darkness approaches. In the desert, the transition from day to night happens quickly, dramatically. One moment the stones are radiating accumulated heat, the next they're cool to the touch. The sky transforms from pale blue to deep indigo, and stars begin to emerge, the same stars that guided the builders who created this monument. We're going to explore every dimension of this structure. Each detail reveals something about the people who built this, the civilization that demanded it, and the mystery that still surrounds it. We'll walk through its history, its construction, its purpose, and its legacy. We'll descend into its hidden chambers and climb through its narrow passages. We'll examine what we know and acknowledge what remains unknown. Let's start at the beginning, in a world so different from ours that it requires imagination just to glimpse it. A world where the Nile flooded predictably each year, where the pharaoh was literally divine, where death wasn't an ending but a transformation into something greater. Chapter 1. The world before the pyramid context itself is where we must begin. The Great Pyramid was built during Egypt's 4th dynasty, a period known as the Old Kingdom. When Egyptian civilization had already been thriving for centuries, this wasn't the dawn of their culture. This was their golden age, their moment of supreme confidence and capability. The Nile Valley during this period was unlike anywhere else on Earth. Annual floods deposited rich silt across the farmland, creating abundance that freed people to pursue specialization. Farmers, yes, but also scribes, priests, craftsmen, administrators, engineers. A complex society with sophisticated bureaucracy, advanced mathematics, and deep religious traditions. The pyramids at Giza were not the first pyramids Egypt had built. By the time Khufu commissioned his great monument, Egyptian engineers had been refining pyramid construction for generations. They had learned from earlier attempts, both successful and failed. The bent pyramid at Dashur shows where angles were adjusted mid-construction. The pyramid at Meidum reveals what happens when outer casing stones aren't properly supported. Each previous structure taught lessons that informed what would be built at Giza. The name we need to remember is Khufu. In Greek histories he's called Cheops, but to his people he was Khufu, the second pharaoh of the 4th dynasty. He ruled sometime around 2600 years before the Common Era, though exact dates remain debated by scholars who work with fragmentary records and astronomical calculations. What isn't debated is his ambition, his vision, his determination to create something unprecedented. Khufu inherited a stable kingdom from his father Sneferu, who had himself built multiple pyramids. The dynasty was at its peak, with resources flowing into the royal treasury, a well-organized administrative system, and the accumulated knowledge of previous generations of builders. Khufu had the means, the expertise, and the divine mandate to attempt something extraordinary. But to understand why the pyramid exists, you must understand how ancient Egyptians viewed their kings. This wasn't a matter of politics or governance as we understand those concepts. Pharaohs weren't simply political leaders who happened to enjoy luxurious lifestyles and commanded armies. They were living gods, divine intermediaries between the mortal realm and the eternal one. When a pharaoh spoke, it was the voice of divinity made manifest in human form. The pharaoh maintained Ma'at, the cosmic order that kept chaos at bay. Without the pharaoh, the Nile might not flood, the sun might not rise, the stars might cease their orderly procession across the sky. This wasn't metaphor to the ancient Egyptians. This was understood as literal truth, as fundamental to the functioning of reality as gravity is to our understanding of the universe. When a pharaoh died, he didn't simply cease to exist, didn't merely become a memory or a corpse. He transformed, became one with the gods, particularly with Ra, the sun god who travelled across the sky each day in his solar bark, bringing light and life to the world. The pharaoh's death was his apotheosis, his assumption into the divine realm where he would continue to serve as a bridge between worlds. This belief explains something that otherwise seems inexplicable. If a pharaoh was divine, his tomb wasn't just a burial place, wasn't simply a container for a body. It was a transformation chamber, a cosmic launch pad, a permanent dwelling for a god. This explains why Egyptian royalty poured resources into tombs that dwarfed their palaces. The palace was temporary, a place for the brief mortal phase of a divine existence. The tomb was forever, or at least as close to forever as human effort could achieve. Look beyond just Khufu's pyramid for a moment. The entire Giza plateau became a sacred landscape over the course of several generations. Eventually it would hold 3 major pyramids, multiple smaller pyramids for queens, temples both mortuary and valley, causeways connecting these elements, and an entire infrastructure dedicated to the afterlife. This was a city for the dead, but also a factory for eternity, a place where the living laboured to ensure the divine order continued beyond death. Mortuary temples at the pyramid's bases served as interfaces between the living and the dead. Priests performed daily rituals, offerings of food and incense, recitations of sacred texts. These weren't symbolic gestures. The Egyptians believed the pharaoh's spirit needed these offerings, that the rituals sustained the transformed god-king in his eternal existence. The pyramid shape itself wasn't arbitrary. It wasn't chosen simply because it was stable or impressive. The form represented the primordial mound that emerged from the waters of chaos at creation, according to Egyptian mythology. In the beginning, there was only none, the primordial ocean, formless and dark. From these waters rose the first land, the first solid thing in existence, and from this mound the creator god Atum brought forth all of creation. Every pyramid echoed this cosmic moment of creation. But pyramids also represented something else, something visible in the sky. They were stone representations of the sun's rays breaking through clouds, creating a stairway between earth and heaven. Stand in the desert when storm clouds gather and you'll see them, those dramatic rays of light piercing through, creating visible paths from sky to ground. The pyramid made these rays permanent, made them solid, made them a reliable path for the pharaoh's soul to ascend. Every angle had meaning. Every orientation served purpose. Nothing about the pyramid's design was random or merely aesthetic. The slope of the sides, the alignment of the corners, the positioning on the plateau, all of these emerged from careful planning that integrated mathematical precision with spiritual significance. The pyramid required years of preparation before a single stone was quarried. Site selection came first. Why this particular spot on the plateau? Visibility certainly, bedrock quality absolutely, but also astronomical considerations, ritual appropriateness, symbolic meaning. The ancient Egyptians approached this project with the same methodical precision that modern engineers would recognize, just with different tools and different motivations. Astronomical observations determined orientation. Priests and astronomers spent nights watching the stars, marking their positions, calculating alignments. Landscape surveys mapped the terrain and calculated volumes. Scribes recorded measurements, tracked resources, projected timelines. Resource calculations determined how much stone would be needed, how many workers, how much food to feed them, how many tools would wear out and need replacement. Labour organisation required creating entirely new administrative structures. Overseer positions needed to be created and filled. Supply chains had to be established. Living quarters for workers had to be built. Bakeries and breweries had to be constructed to feed the workforce. The pyramids shaped Egypt before construction even began. While we can't pinpoint the exact year construction began, we know it was during Khufu's reign, which lasted approximately 23 years according to ancient king lists. Some estimates suggest the pyramid took 20 to 30 years to complete, which means planning likely began before Khufu even took the throne, during his father's reign, when succession was being prepared and the young prince was learning what would be expected of him. This wasn't just about creating something big, it wasn't about vanity or showing off. It was about creating something perfect, something that would speak to eternity about Egyptian capability, about divine order, about the triumph of Ma'at over chaos. Ma'at was the Egyptian concept of cosmic order and balance, truth and justice, the fundamental rightness of things. The pyramid embodied Ma'at in stone, imposed order onto the landscape, created permanence in a world of change. By the time the first stone was laid, this project had already changed Egypt. It had required reorganization of labour patterns, development of new techniques, creation of infrastructure for transport and logistics. The pyramid shaped the civilization even before it shaped the skyline, demanded innovations that would outlast the construction itself. Chapter 2: A mountain built by humans. When you first see it in person, the scale hits you physically. The Great Pyramid originally stood 481 feet tall. To put that gently in perspective, it remained the tallest human-made structure on Earth for over 3,800 years. Think about that. 38 centuries of human progress, and nothing surpassed it until medieval European cathedrals finally exceeded its height. Try to imagine that span of time. The pyramid was already ancient when the Parthenon was built in Athens. It was already a tourist attraction when Rome was founding its empire. It had stood for over 2,000 years before the first words of the New Testament were written. And through all that time, through the rise and fall of countless civilizations, it remained the tallest thing humans had ever built. Today, the pyramid stands at 455 feet. The difference represents the loss of the pyramidion, the capstone that once crowned the structure, along with settling and erosion over millennia. Even diminished, it dominates the landscape. Modern Cairo has grown around it, buildings creeping closer to the plateau's edge, but the pyramid still commands attention. You can see it from miles away, rising above the urban sprawl. To truly grasp the scale, you need to walk around it. Each side of the base measures approximately 756 feet. The pyramid covers just over 13 acres of desert. To visualize this, imagine walking the perimeter. At a casual pace, it would take you nearly 15 minutes to circle the structure once. 15 minutes of walking past uninterrupted stone and you're back where you started. Stand at one corner and try to see the opposite corner. You can't. The distance is too great, the perspective too vast. The pyramid doesn't just occupy space, it defines it, creates its own gravitational center on the landscape. Those four base sides aren't just roughly equal, they're equal to within inches across lengths of more than 700 feet. The base is almost perfectly level, with variations measured in fractions of an inch. This level of accuracy, achieved without modern instruments, without laser levels or GPS, without even the magnetic compass, remains genuinely remarkable. The surveyors who laid out the pyramid's foundation worked with water levels, measuring rods, and astronomical observations. They created a platform so level that modern instruments struggle to detect variations. On a structure covering 13 acres, this precision borders on the inexplicable. The pyramid contains approximately 2.3 million stone blocks, with a total mass estimated at around 5.9 million tons. To compare, that's roughly the weight of 16 Empire State Buildings. It's a mountain of stone, assembled block by block, each piece cut, transported, and positioned with care. Think about that number, 2.3 million blocks. If you spent 1 second looking at each block, it would take you over 26 days of continuous observation to see them all. And the ancient Egyptians didn't just look at them. They quarried them, shaped them, moved them, and placed them. The average block weighs about 2.5 tons, roughly the weight of a large SUV, but this average conceals variation. Some blocks weigh less than a ton, others weigh significantly more. The pyramid isn't uniform. Its interior contains chambers, passages, and structural features that require different stone sizes. The largest granite blocks, used in the king's chamber and the relieving chambers above it, weigh between 25 and 80 tons each. These massive pieces of stone weren't placed at ground level where you could simply roll or slide them into position. They were lifted and positioned high within the structure's interior, fitted with extraordinary precision. Imagine moving an 80-ton granite block. That's heavier than most modern trucks. Now imagine lifting it 100 feet into the air and positioning it exactly where it needs to be, aligning it perfectly with adjacent blocks. The ancient Egyptians did this repeatedly, without cranes, without hydraulics, without any of the machinery we consider essential for such work. The blocks fit together with joints so tight that you often can't slip a piece of paper between them. This wasn't achieved with mortar filling gaps. The stones themselves were cut and placed with extraordinary precision. Run your hand along a joint between blocks and you'll feel how seamlessly they meet. The precision is tactile, physical, undeniable. From its completion around 2560 BCE until Lincoln Cathedral's central tower was completed in 1311 CE, no structure exceeded the Great Pyramid's height. That's 3,871 years of supremacy. No other building in history has held that record for anywhere close to that length of time. The pyramid defined the limits of human architectural ambition for millennia. The pyramid's internal volume has been calculated at around 2.6 million cubic meters. It's mostly solid stone, with relatively small interior spaces comprising the passages and chambers. The ratio of solid mass to empty space is extraordinary. This isn't a hollow shell. It's a mountain, with narrow corridors carved through it. The pyramid's faces rise at an angle of 51 degrees, 51 minutes. This specific angle wasn't chosen randomly. It relates to both aesthetic proportions and structural stability, creating a profile that has successfully supported the massive weight above for over 4,000 years. Steeper, and the structure might be unstable. Shallower, and it would cover an impossibly large footprint. This angle represents the optimal solution to multiple engineering challenges. Each face of the pyramid covers about 5.5 acres of sloping stone. Originally, with the polished casing stones in place, these faces would have presented smooth, nearly seamless surfaces reflecting sunlight like mirrors. Imagine 5.5 acres of polished white limestone tilted at 51 degrees catching the Egyptian sun. The visual effect would have been overwhelming. The ratio of the pyramid's perimeter to its height approximates 2 times pi, a mathematical constant. Whether this was intentional or coincidental remains debated, but it demonstrates the sophisticated geometric understanding of the builders. Even if they didn't conceptualize pi as we do, they clearly understood the relationships between angles, heights, and perimeters. The pyramid has survived major earthquakes that destroyed other structures in the region. Its form, with a broad base and tapering sides, distributes weight efficiently and provides inherent seismic resistance. When the ground shakes, the pyramid flexes slightly, absorbing and dissipating energy. Its mass provides stability, its shape provides strength. All this mass, all this precision, all this scale required not just vision but practical solutions to impossible-seeming problems. How do you actually build such a thing? How do you organize the work? How do you move the stones? How do you ensure accuracy? These questions lead us to the next chapter, to the practical realities of construction. Chapter 3. How stone became structure. The bulk of the pyramid's limestone came from quarries located right on the Giza plateau itself. The ancient Egyptians didn't transport millions of tons of stone from distant locations. They cut it from the bedrock beneath and around the construction site. You can still see the quarry marks. In the plateau's surface, evidence of where stone was systematically removed. These quarries became part of the construction site's landscape. As workers cut blocks from the ground, they created depressions, channels, ramps. The plateau was reshaped by the act of building, transformed from natural bedrock into a worked landscape of human intention. While local limestone formed the pyramid's core and most of its mass, 2 special types of stone came from elsewhere. White Tura limestone used for the exterior casing was quarried across the Nile River and transported by barge during the annual flood when the river was high. Red Aswan granite, used for the king's chamber and internal structural elements, came from quarries over 500 miles to the south, a journey that would have taken weeks. The transport of Aswan granite represents a logistical achievement almost as impressive as the pyramid itself. These massive blocks had to be cut from living rock in Upper Egypt, loaded onto barges capable of supporting enormous weight, floated hundreds of miles down the Nile, offloaded at Giza, and then moved from the river to the plateau and up into position within the pyramid's interior. For the local limestone, workers cut blocks free from the bedrock, then moved them using wooden sledges pulled by teams of men. Recent experiments have demonstrated that wetting the sand in front of the sledges reduced friction dramatically, making it possible to move massive stones with human power alone. Water transformed sand from an impediment into a lubricant. This technique appears simple, but represents sophisticated understanding of physics. The workers knew that dry sand would create friction, causing the sledge to dig in and resist movement. Wet sand, however, compacts and smooths, allowing the sledge to glide. Ancient tomb paintings show workers pouring water in front of sledges, depicting this technique in action. The pyramid wasn't built by slaves. Evidence from worker villages, graffiti left by construction crews, and analysis of burial sites indicates the labourers were paid workers, organised into rotating shifts. Many were farmers who worked on the pyramid during flood season, when agricultural work was impossible. They came to Giza, laboured for a period, and then returned to their farms. This wasn't forced labour. This was organised public works, a civic duty that also provided wages and purpose during the agricultural off-season. Calculations based on the number of stones, the time available, and the physical limitations of the work suggest a permanent workforce of around 20,000 to 30,000 people, with possible peak periods employing more. This workforce would have included not just stone movers but also quarrymen, tool makers, rope manufacturers, carpenters, supervisors, scribes, bakers, brewers, and countless other specializations. The pyramid required an entire support economy. Crews had names, left graffiti, proclaiming their achievements, and appear to have engaged in friendly competition. One crew called themselves Friends of Khufu. Another was Drunkards of Menkaure. These weren't anonymous slaves toiling in misery. They were organised teams with identity and pride, workers who saw themselves as part of something greater than themselves. The graffiti they left inside the pyramid, marks invisible to anyone not exploring the structure's interior spaces, reveals their pride. They marked which crew had placed which blocks, recorded their names, left evidence of their existence. These marks weren't for public display, they were for themselves, for their gods, for eternity. Archaeological excavations have uncovered worker villages near the pyramid site, complete with bakeries, breweries, workshops, and sleeping quarters. These workers ate well, primarily bread, beer, and meat, suggesting they were valued, not exploited. The bakeries could produce enough bread to feed thousands. The breweries produced beer, which was a staple beverage safer to drink than water. Evidence suggests workers received medical care, with healed fractures showing treatment and recovery periods. The primary stone-cutting tools were copper chisels and saws, along with stone hammers. Copper is soft compared to modern steel, requiring frequent sharpening and replacement, but it was sufficient for cutting limestone when combined with abrasive sand. Workers would saw into limestone using copper blades, pouring sand and water into the cut to create an abrasive slurry that did the actual cutting. For harder stones like granite, different techniques were necessary. Workers used dolerite hammerstones, extraordinarily hard igneous rock, to pound and shape granite blocks. This was slow, painstaking work, but effective. The precision achieved in granite cutting, particularly in the King's Chamber, demonstrates mastery of the material. To achieve the tight joints between blocks, workers likely used a method of repeatedly placing stones, marking high points with red ochre, removing the stone, grinding down the marked areas, and repeating until the fit was perfect. This trial and error approach requires patience, but produces remarkable results. Analysis shows that thin layers of gypsum mortar were used between some stones, but not to hold them together. The mortar served more as a lubricant during positioning, and may have helped with fine adjustments. The weight of the stones above provides the real structural bond. Once in place, the blocks don't need mortar. Gravity and precision do the work. How the Egyptians lifted stones to increasing heights remains partially uncertain, but most theories involve some form of ramping system. Straight ramps extending from ground level to the pyramid's top would require enormous amounts of material and would need to be lengthened as the pyramid rose. Spiral ramps wrapping around the pyramid's exterior could work but would complicate corner construction. Internal ramps built into the pyramid structure remain possible but unproven. Evidence exists for all these approaches, suggesting the Egyptians may have used different methods at different stages of construction. Pragmatism likely trumped dogmatic adherence to a single technique. If one approach worked better for a particular challenge, they used it. Despite everything we know, significant questions remain about specific construction techniques. The absence of detailed construction records from the period means we're often working backward from the finished product, deducing methods from results. This isn't failure of archaeology. This is the nature of studying a civilization that didn't document their building techniques because they were common knowledge at the time. The pyramid's construction required not just labour, but logistics, coordination, resource management and planning that would challenge modern project managers. Feeding 30,000 workers daily meant producing thousands of loaves of bread and gallons of beer every day. Maintaining tool supplies required a steady production of copper implements. Coordinating stone delivery from multiple quarries demanded scheduling and communication systems. If the pyramid took 20 years to complete and contains 2.3 million blocks, workers would have needed to place approximately 315 blocks per day, every day, for 2 decades. This seems impossible until you remember this wasn't sequential. Multiple teams worked simultaneously on different sections. Different quarries provided stone concurrently. The project progressed on many fronts at once. All this effort, all this organisation, all this daily labour over decades served not just to create mass, but to create alignment, to achieve something beyond mere construction. The pyramid wasn't just big, it was oriented, aligned, positioned according to principles that connected earth to sky. Chapter 4: Order in the Stars. The Great Pyramid is aligned to true north with an accuracy of about 4 arc minutes, or 1/15 of a single degree. This precision exceeded the capabilities of compasses, which the ancient Egyptians didn't possess. They achieved this alignment through careful observation of the stars, a technique that required patience, mathematical understanding, and sophisticated astronomical knowledge. The most likely method involved observing circumpolar stars, stars that never set below the horizon as they wheel around the celestial pole. By tracking a star's rising and setting points on an artificial horizon and bisecting the angle between them, ancient astronomers could determine true north with extraordinary accuracy. This required building observation platforms, marking positions, performing calculations, and checking results multiple times. Some researchers have proposed that the 3 pyramids of Giza align with the 3 stars of Orion's belt, a constellation, the Egyptians associated with Osiris, god of the afterlife. While this correlation has been debated and remains controversial in academic circles, the Egyptians definitely viewed the sky as a map of the divine realm. Stars weren't just points of light, they were gods, destinations, the architecture of heaven. The 4 faces of the pyramid align precisely with the 4 cardinal directions: north, south, east, and west. This ensured the structure harmonized with the sun's daily journey across the sky, reinforcing the connection between the pharaoh and the sun god Ra. Each face caught the sun at different times, creating a daily cycle of light and shadow that echoed the sun god's journey. 2 narrow shafts extend from the king's chamber, one pointing north, one south. Similar shafts exist in the queen's chamber, though these don't extend all the way through the pyramid's masonry. These weren't ventilation shafts in any practical sense. Air circulation wasn't necessary in a tomb. They appear to have had astronomical or spiritual significance, possibly representing pathways for the pharaoh's soul to ascend to specific stars. The southern shaft from the king's chamber, when the pyramid was built, pointed directly at Al-Nitak, the brightest star in Orion's belt during its culmination at the meridian. Whether this was intentional remains debated, but the precision of the alignment is undeniable. The shaft isn't just vaguely pointing south. It's aimed at a specific celestial target. The northern shaft from the king's chamber, at the time of construction, aligned with Thuban, then the pole star in the constellation Draco. This alignment would change over time due to Earth's axial precession, the slow wobble of our planet's rotation that causes the position of the pole star to shift over thousands of years. This makes the shaft a timestamp, evidence of exactly when the pyramid was built. The Egyptian concept of Ma'at, cosmic order and balance, pervades every aspect of the pyramid's design. The precise alignments weren't just technical achievements, weren't simply the result of engineers showing off their skills. They represented the imposition of divine order onto the physical world, ensuring the structure harmonized with eternal cosmic patterns. The pyramid was meant to function not just as a building, but as a cosmological instrument, a physical embodiment of the relationship between earth and heaven. While we can measure these alignments precisely today using modern instruments, we can't always know their exact significance to the ancient builders. We're looking at their choices through our modern understanding of astronomy, which may not fully capture their spiritual and cosmological framework. They saw meaning in the stars that goes beyond our cataloguing of positions and magnitudes. We've examined the pyramid from outside, traced its connections to earth and sky, explored its relationship to cosmic order. Now it's time to enter to explore the hidden chambers carved into millions of tons of stone, to walk passages that have existed in darkness for millennia. Chapter 5. Inside the Pyramid. The original entrance is located on the north face, about 55 feet above ground level. This wasn't the entrance tourists use today. That was created by workers digging for treasure in the 9th century, breaking through the masonry in an attempt to reach whatever riches they imagined lay within. The hole they created bypasses the pyramid's original entrance system, providing direct access to the interior. From the original entrance, a narrow corridor slopes downward at an angle of 26 degrees, cutting first through the pyramid's masonry, then through the bedrock beneath. This passage is only about 3.5 feet tall, forcing anyone traversing it to stoop or crawl. The walls are smooth, the angle constant, the construction precise even in this hidden space where no one was meant to see. The descending passage eventually opens into a rough-cut chamber carved from bedrock, located about 90 feet below the pyramid's base. This chamber appears unfinished, with an irregular floor and a shaft descending even deeper into the bedrock, extending down into darkness. Its purpose remains unclear. Was it abandoned when plans changed? Was it always meant to be unfinished, representing the underworld's chaos in contrast to the finished chambers above? We don't know. About 60 feet from the entrance, a different passage branches upward from the descending corridor, also at an angle of 26 degrees, but climbing into the pyramid's interior rather than descending beneath it. For centuries, this passage was concealed by a fitted stone plug, hiding the pyramid's true interior from anyone who entered through the north face. The passage was invisible, a secret route to chambers above. The ascending passage is narrow and low, barely allowing passage, maintaining the same uncomfortable dimensions as the descending corridor. You can't walk upright, you can't move quickly. Every foot of progress requires effort and attention. But this passage climbs toward the pyramid's heart, rising through solid masonry toward something extraordinary. The ascending passage opens into the Grand Gallery, one of the ancient world's most remarkable architectural achievements. This corbelled passage soars 28 feet high, while maintaining the same upward angle as the ascending passage. The walls step inward as they rise, creating a narrow ceiling despite the impressive height. The effect is cathedral-like, unexpected in a space that spends most of its existence in complete darkness. The Grand Gallery's function remains debated. Some theories suggest it housed sliding granite blocks that would seal the ascending passage after the pharaoh's burial. Others propose it served a ceremonial function during the pyramid's construction and consecration. The space feels too grand, too carefully constructed to serve a purely utilitarian purpose, yet its exact role in the pyramid's design eludes certain explanation. At the top of the Grand Gallery, through a narrow antechamber with granite portcullis blocks that could have sealed the chamber beyond, lies the king's chamber. This room measures about 34 feet long, 17 feet wide and 19 feet tall. Every surface is lined with red Aswan granite, brought from quarries over 500 miles to the south. The stone's polished surface catches light, reflects sound, creates an environment unlike anywhere else in the pyramid. In the king's chamber sits a rectangular granite box, slightly larger than a human body, with one corner broken. This is assumed to be Khufu's sarcophagus, though no body or burial goods have ever been found within the pyramid. The lid is missing. The interior is empty. Whether it was robbed in antiquity or never used remains unknown. Some argue the pyramid was looted before historical records began. Others suggest it never functioned as a tomb at all, that its purpose was symbolic or ceremonial rather than practical. Unlike the treasure-filled tomb of Tutankhamun discovered by Howard Carter in the Valley of the Kings, the Great Pyramid has yielded no mummy, no grave goods, no definitive proof it ever served as an actual burial site. This absence has fueled centuries of speculation about the pyramid's true purpose. spawning theories ranging from astronomical observatory to power plant to grain storage. The simplest explanation remains that it was robbed thoroughly in antiquity, but the complete absence of evidence makes certainty impossible. Returning to the ascending passage, taking a different route this time, we find a horizontal passage branching off about halfway up. This leads to what's known as the Queen's Chamber, though no evidence suggests it was intended for a queen. The name is a modern convention based on mistaken assumptions about Egyptian burial practices. The Queen's Chamber sits almost exactly on the pyramid's east-west centerline. It measures about 17 feet square and 20 feet tall, with a pointed corbelled ceiling similar in construction to the Grand Gallery, though much smaller in scale. A niche is cut into the eastern wall, its purpose unknown. Was it meant to hold a statue, an offering? Did it serve some function we can't reconstruct from the empty cavity that remains? The floor of the Queen's Chamber remains rough and unlevelled, suggesting the chamber may have been abandoned before completion. Whether this represents a change in plans, an intentional choice to leave it unfinished, or simply work interrupted by Khufu's death and burial, we cannot say with certainty. Above the King's Chamber, explorers in the early 19th century discovered 5 additional chambers stacked vertically. These weren't designed for access. There are no entrances from the normal passage system. They were discovered by breaking through from the Grand Gallery, creating holes in the masonry to see what lay beyond. These chambers serve as stress-relieving structures, distributing the immense weight of the pyramid above so it doesn't crush the King's Chamber below. The relieving chambers are constructed of massive granite beams laid horizontally, creating open spaces between them. The topmost chamber has a pointed limestone roof, designed to deflect weight outward to the pyramid's sides. Together, these chambers have protected the King's Chamber from collapse for over 4,000 years. Without them, the weight would have crushed the chamber below, reducing it to rubble. The King's Chamber has unusual acoustic properties. Sound resonates within the granite walls in specific ways, creating harmonics and echoes that transform simple sounds into something more complex. Whether this was intentional or coincidental remains debated. Some researchers have experimented with chanting and musical instruments in the chamber, noting unusual resonances. Did ancient Egyptians use this space for ritual purposes involving sound? We can only speculate. We've explored the interior, walked the passages, stood in the chambers, but we've only seen the pyramid as it exists today, stripped of its original covering, weathered by millennia. To understand how it once appeared, we must reconstruct what was lost. Chapter 6. The Lost Skin of Light. Originally, the entire structure was covered in polished white Tura limestone casing stones. These weren't rough blocks like those visible today, weren't the weathered stepped surfaces that tourists photograph. They were precisely cut, polished to a near-mirror finish, and fitted together with joints measured in fractions of an inch. The pyramid wasn't rough, it was smooth. The visual effect of the polished casing would have been transformative. When new, the pyramid didn't look like a stepped stone structure, didn't reveal the internal construction. It appeared as a smooth, gleaming surface, its polished faces reflecting sunlight with eye-searing intensity. Early observers described it as appearing to be made of light itself, a beacon visible for miles. Imagine sunrise at Giza. As the sun crested the eastern horizon, the pyramid's eastern face would catch the first rays, transforming into a blazing triangle of reflected light. The effect would have been visible for miles across the Nile Delta, announcing the presence of divine power made manifest in stone. As the sun climbed, different faces would catch the light, creating a daily cycle of illumination that echoed the sun god's journey. In the clear desert air, the polished pyramid would have been visible from extraordinary distances. Travellers approaching Cairo from any direction would have seen the pyramids long before reaching them, their white surfaces standing in stark contrast to the golden desert sand. They would have appeared to float above the horizon, shimmering in the heat haze, otherworldly in their perfection. The casing stones came from Tura, a limestone quarry across the Nile from Giza. Tura limestone is finer grained and whiter than the local limestone, making it ideal for a polished finish. Transporting these precisely cut stones across the river and up to the pyramid site represented a significant logistical achievement. Each stone had to be protected during transport to prevent damage to its polished surface. Over centuries, and particularly after a major earthquake in the 14th century loosened many casing stones, the polished covering was systematically stripped away. Medieval builders used the fine limestone to construct mosques and buildings in Cairo. The pyramid became a quarry, its outer skin harvested to build other structures. What took decades to construct was dismantled over centuries of opportunistic stone harvesting. A few casing stones remain in place at the pyramid's base, protected by accumulated debris and fallen blocks. These fragments allow us to see the original surface treatment, confirm descriptions from earlier observers, demonstrate the precision of the cutting and polishing. Running your hand along one of these surviving stones, you can feel how smooth it is, how carefully finished, how different from the rough core blocks now exposed. The pyramidion, the capstone that once crowned the pyramid, was likely covered in gold or electrum, a gold-silver alloy. This would have made the pyramid's peak shine even more brilliantly than its white sides, marking the convergence point of the four faces and the symbolic link between earth and heaven. The golden cap would have caught the sun's first and last rays each day, visible as a point of light long before the rest of the pyramid emerged from darkness. The casing stones weren't just cut and polished. Each one was shaped to fit its specific position on the pyramid's face, accounting for the slight curve of each face and ensuring the smooth transition from base to apex. This required mathematical calculation for each stone's angle and precise execution in cutting. Each of the approximately 144,000 casing stones was unique. Stripped of its casing, the pyramid looks ancient, weathered, mysterious in its roughness. But we must remember, for most of its existence it looked new, intentional, triumphant. What we see today is the skeleton, the core exposed. What the ancients saw was the finished achievement, perfect and gleaming, a monument that announced Egyptian power and divine order to anyone who saw it. The transformation from polished magnificence to rough pyramid took centuries, happening gradually as stone was removed for other projects. By the time Napoleon saw the pyramids in 1798, they already looked much as they do today. Their covering long gone, their original appearance preserved only in written descriptions and the few fragments still clinging to the base. Chapter 7. Misunderstood. For centuries, the pyramid wasn't built by slaves. This misconception, popularized by ancient historians like Herodotus, who visited Egypt 2,000 years after construction, and reinforced by biblical narratives and Hollywood films, contradicts all archaeological evidence. The builders were skilled workers, compensated for their labor, proud of their achievement. The persistence of this myth says more about later cultures' assumptions than about ancient Egyptian reality. The precision and scale of the pyramid have led some to claim it couldn't have been built by ancient humans and must represent alien intervention or lost advanced civilizations. These claims ignore both the archaeological evidence of Egyptian capability and rest on the assumption that ancient non-European peoples couldn't achieve sophisticated engineering. The pyramid is impressive precisely because humans built it, because it represents what organized, sustained human effort can accomplish. When classical Greek and Roman civilizations encountered the pyramids, Egypt's pyramid-building age was already more ancient to them than Rome is to us. They marveled at the structures, but often misunderstood their purpose, ascribing them to vanity and hubris rather than religious devotion. Herodotus recorded stories about Khufu that portrayed him as a tyrant who enslaved his people, narratives that tell us more about Greek assumptions than Egyptian reality. During the Islamic medieval period, some believed the pyramids contained vast treasures or ancient wisdom preserved from before the Great Flood. This led to multiple attempts to break into them, including the creation of the entrance tourists use today, forced through the masonry in search of riches that didn't exist. These treasure hunters did permanent damage, creating passages that bypassed the pyramid's original entrance system. Various claims assert the pyramid encodes pi, the golden ratio phi, the speed of light, the Earth's dimensions, or other constants. While some proportional relationships exist, attributing modern mathematical constants to ancient builders requires selective measurement and often ignores the evidence of how such proportions actually arose from practical building decisions and aesthetic choices rather than intentional encoding of universal constants. The ratio of the pyramid's perimeter to its height approximates 2 times pi. However, this can arise naturally from using a rolling drum to measure and establish the angle, a technique that would have been available to ancient builders without requiring knowledge of pi as an abstract constant. The relationship is real, but it doesn't necessarily indicate intentional encoding of mathematical knowledge. Some claim the pyramid's proportions reflect the golden ratio, phi, a number found throughout nature and art. While certain measurements create ratios close to phi, these can be explained by the pyramid's angle and the geometric properties that angle creates, rather than intentional encoding. The Egyptians had sophisticated mathematical knowledge, but we must be careful about projecting our mathematical concepts onto their design choices. Serious scientific study of the pyramids began in the 19th century, when scholars like Jean-François Champollion's decipherment of hieroglyphics allowed researchers to actually read ancient Egyptian texts. This transformed understanding from speculation to evidence-based analysis. For the first time, researchers could read what Egyptians wrote about themselves, their beliefs, their practices. The 20th century brought systematic excavation, careful documentation, and scientific analysis. Rather than seeking treasure or mysteries, researchers focused on understanding the pyramids in their cultural and historical context. Excavations of worker villages, analysis of tools and techniques, study of contemporary texts and records, all built a comprehensive picture of how and why the pyramids were built. Despite centuries of study, significant questions remain. This doesn't validate wild theories or suggest hidden knowledge. It simply reflects the reality that ancient Egypt predates detailed written construction records, leaving us to deduce techniques from physical evidence and fragmentary texts. Mystery isn't proof of the impossible. It's just the natural state of studying the distant past. Chapter 8. Modern Discoveries. In recent decades, researchers have begun using non-invasive scanning techniques to study the pyramid's interior without drilling or damaging the structure. These methods include muon radiography, which uses cosmic ray particles to create density maps, infrared thermography, which reveals temperature variations indicating hidden chambers, and three-dimensional laser scanning, which creates precise models of the pyramid's geometry. The Scan Pyramids project, beginning in 2015, used cosmic ray muon detectors to create images of the pyramid's internal density. Muons are particles created when cosmic rays strike Earth's atmosphere. They penetrate stone but are partially absorbed based on density, allowing researchers to map internal voids. The technique is slow, requiring months of data collection, but completely non-invasive. In 2017, the Scan Pyramids team announced the detection of a large void above the Grand Gallery. This space, approximately 100 feet long, was previously unknown. Its purpose and contents remain mysterious, as it's inaccessible without creating new passages through the pyramid, something researchers are unwilling to do. The void exists. We know its approximate size and location. What it contains remains unknown. Small robots have been sent through the narrow shafts extending from the King's Chamber and Queen's Chamber, carrying cameras to document areas humans can't reach. These explorations have revealed previously unknown chambers and features, small spaces carved into the pyramid's interior. Each discovery raises new questions about the pyramid's design and purpose. The robots exploring the shafts from the Queen's Chamber encountered stone doors with copper handles. When carefully drilled and explored, these led to small spaces, then additional doors. What lies beyond remains unknown. Each answer reveals new mysteries, new spaces we didn't know existed. Modern archaeology moves slowly, prioritizing preservation over discovery. Each intervention must be carefully planned to minimize damage. This means some mysteries may remain unsolved for years or decades until technology advances sufficiently. We could find answers faster if we were willing to break through walls and drill into chambers, but the cost would be irreversible damage to an irreplaceable structure. New discoveries in Egypt continue regularly, not just at Giza, but throughout the Nile Valley. Ancient settlements, quarries, worker villages, and texts continue to emerge from the sand, each adding pieces to our understanding of the civilization that built the pyramids. Each new tomb discovered, each papyrus translated, each settlement excavated, adds context to the pyramids themselves. The pyramids of Giza, along with the entire Memphis necropolis, were designated a UNESCO World Heritage Site in 1979. This classification provides international protection and recognises the pyramids as heritage belonging to all humanity, not just Egypt. The designation comes with responsibilities for preservation and careful management. Millions of people visit the pyramids annually, creating both economic benefit and conservation challenges. Balancing access with protection requires constant effort. Human presence accelerates deterioration through humidity from breath, erosion from touch, simple physical contact. Managing tourism while preserving the monuments requires ongoing vigilance and careful planning. Desert conditions have preserved the pyramids better than any other environment could, but they're not immune to environmental damage. Wind erosion gradually wears away exposed surfaces. Salt crystallization, when rare moisture penetrates the stone and then evaporates, can crack and crumble the limestone. Occasional rain, though rare, can cause damage. Temperature fluctuations between scorching days and cool nights create expansion and contraction that slowly wears the stone. Chapter 9. The Pyramid Today. The Great Pyramid has stood for over 4,500 years. It predates classical Greece by 2,000 years. It was already ancient when Rome was founded. It stood finished for over 1,000 years before the first books of the Hebrew Bible were written. Try to grasp that span of time. 45 centuries, more than half of recorded human history. The pyramid has survived countless earthquakes, including major tremors that destroyed other structures in the region. Its form provides inherent stability, and the precision of its construction has allowed it to flex and settle without catastrophic failure. When the ground shakes, the pyramid absorbs the energy, moves slightly, then settles back into stability. Its mass is its protection. Despite modern Cairo's expansion, despite the sprawl of buildings that now reach nearly to the plateau's edge, the pyramid still dominates the landscape. From many parts of Cairo, you can look up and see it, exactly where it's always been, unchanged while everything around it transforms. The city grows, changes, rebuilds itself generation after generation, while the pyramid remains. The pyramid represents many things to many people: ancient achievement, human ambition, religious devotion, engineering triumph, historical mystery. It's been called the machine of eternity, the mountain of light, the throne of Pharaoh. But perhaps most fundamentally, it's evidence that humans, working together with purpose and dedication, can create something that transcends their individual lifespans and speaks across millennia. Tonight, the desert wind still moves across the Giza plateau. The stars wheel overhead in patterns that have shifted since the pyramid was new. The pole star no longer where it was when those astronomical shafts were aimed. Sand accumulates and is blown away, accumulates again. The sun rises, blazes across the sky, and sets as it has done more than 1.6 million times since the final block was placed. The pyramid doesn't need us to understand it. It doesn't require our theories or our amazement. It existed for thousands of years before modern archaeology, and it will exist long after we're gone. But we're drawn to it anyway, generation after generation, seeking meaning in its massive permanence, finding questions in its precise angles. As you drift towards sleep tonight, imagine standing at the pyramid's base as darkness settles completely. The rough stone rises above you, each block, representing countless hours of human effort. Somewhere within, the king's chamber sits empty, sealed in darkness, unchanged since the last torch was extinguished millennia ago. The grand gallery angles upward through millions of tons of stone. The shafts point towards stars that have shifted in the sky. The pyramid keeps its secrets, Not out of malice or mystery, but simply because it is stone. It cannot speak, it can only stand. And in standing, it reminds us that humans, for all our limitations, for all our brief individual existence, can create something that outlasts empire, outlasts language, outlasts everything but time itself. The desert wind continues its eternal movement across the sand. The pyramid remains, exactly where it has always been, exactly what it has always been, a monument to belief, to effort, to the uniquely human drive to create something eternal. Rest now. The pyramid has stood for 45 centuries. It will still be standing when you wake.